Below is the phase plot for a particular autonomous differential equation. So du by dt is some function g of just u. That's what makes it autonomous. There are no t's to be found anywhere here. If a particular solution, because of course differential equations have infinitely many solutions, but a particular solution satisfies this particular initial condition, so when t is 1, the output of our function u, our solution, is 2, we want to know what is the limit, the long-term behavior of this u of t solution. Okay? So it's like we've solved this dE. Of course, we can't without knowing what g is, but it's like we've solved it and we got a particular solution, and we want to know what's the long-term behavior of that. Unfortunately, we don't need to solve the dE. As long as we got a phase plot for an autonomous differential equation, all you need to know is some value. It doesn't like, we've got u at 1, but u at 1 million would still work. You could figure out the long-term behavior. Okay? How exactly do you do that? Whatever the output value is that you know, you start there on your phase plot. So we know u at 1 is 2. Okay? So remember the u values. We don't care about t. The phase plot does not have a t on it. It's got a u-axis and a derivative axis. So in this case, du by dt on the vertical. But you just start with, okay, we know u is equal to 2 at some point. Does not matter what the t value was. Okay? Now, the phase plot tells us how the u values should change. How is the function changing? Well, that's what's given by the vertical information on the curve. So when u is 2, we can see, okay. At that same moment, du by dt has to be g at 2, which we find is negative. It's a negative value. So u should decrease, which means it should move a little bit over. The u value, if you decrease on a horizontal axis, moves to the left. So we move a little bit over, and maybe we get to like 1.2. And then, looking at that, the derivative is still negative, so we're going to keep going. And what you can do, you don't have to do this sort of piece by piece. You can just say, look, it's going to be negative, 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 negative. We're just going to keep decreasing until we run into an equilibrium solution, which in this case we can see is -1. And so we're just going to keep decreasing and decreasing and decreasing towards -1. Now you can see the g at u values, they're negative, but they're getting smaller, which means you'd be taking smaller and smaller jumps. And so in the long run, you won't get to -1, but in the long run, we can follow the arrow and say, we tend to -1 in the long run. Okay, so there we go. -1 is the limit of this particular solution. Another solution that started, over here at 8 would say, okay, well, the rate of change is positive, so I'm actually going to move this way and would spiral off to infinity. Something that started over here at -3 will keep decreasing and decreasing and decreasing. You sort of just follow the arrows, and the arrows are dictated by whether or not the curve is above or below the axis, because that tells you the rate of change being positive or negative, whether or not you should increase or decrease. And then you just go until you hit an equilibrium solution, or you go to infinity or negative infinity. So in this case, we tend to -1 in the long run.